All right, William, can you hear me okay?
Yeah, we can hear you. How are you?
Great. All right, let's get rolling. So good morning, everyone. I hope you are having a good week. Happy Thursday, almost the weekend. Cannot believe how quickly the semester is going by. I don't know if you guys feel that same way. So nothing sort of all that new from last time. A reminder that there is a practice derivative session tonight. Link is in Moodle. There's only one mini quiz this week and it's on Sunday. So if you haven't already done it, that's totally fine because we haven't even finished the section yet. And then next week we will be finishing up chapter 3 with the last 2 topics. So we're just sort of plugging along and a continuation from our last class. So just as a reminder, let me switch on over the dot cam here. We're talking about the chain rule. So we're talking about how we take derivatives of functions that are made up of composite functions, right? So we've made some sort of composite function, and now we want to figure out the rate of change for that function. And so we have to use the chain rule. So last time we looked at some conceptual examples, and then we looked at the power function form. So when we had something raised to a power, and we also went over the exponential form. So there's one more exponential problem that's an application that we'll start with, and then we'll sort of continue through looking at the other forms that we will need to learn. So here you can see the exponential problems that we did last time. And as we went through those, there were 2 ways we could do this. We could do this with a z substitution, or we could think about this more conceptually to think about how the derivative was found. We did it both ways, but now we want to look at an example of why we might want to be able to find the derivative of a composite exponential function. So we're going to start with this example 4. I'm going to have you try it so you can hopefully remember what we were doing last time. So here we have the demand curve for a product is given by Q equals F of P equals 4,500 e to the negative 0.15 P. And just as a general reminder, if we're talking about a demand curve, what we're trying to figure out is what quantity people will buy if we set a certain price. So if we were to plug in, like a 1 in for P for price, the number that comes out would tell us what is predicted for how many of that item a person would buy. That's what a demand curve tells us. So here, Q is the quantity sold, P is the price in dollars. We want to find and interpret F prime of 6. So the derivative of this function and then plugging in a 6, we want to both find it, but also talk about what it might represent for us. Okay, so take 2 minutes. Feel free to look back at your notes from last time if you need to think about the derivative of an exponential. But again, this is a chain rule because of that number up in the power. We also talked about how to do that algebraically several classes ago. But just see what you can figure out. Feel free to check in with someone with you, and then we'll go over it in about 2 minutes. All right, take about 30 more seconds. All right, so here, when we look at this, we notice that there's this constant in front. And so we have to remember the constant multiple rule. So we're going to keep this 4,500. And then we want to multiply that by the derivative of this e term. So we said when we take the derivative of an exponential, we're going to get the same thing back. But then we have to multiply that by the derivative of the power. So if we look at the power here, we have negative 0.15p. And we have to remember that if we have a linear term, so a number times the variable, that the derivative is just that number, so negative 0.15. Again, with exponentials, the power never changes. What's different is that we're multiplying by something in front. So now we want to simplify this. We can multiply this negative 0.15 times 4,500. So we get negative 675 e to the negative 0.15p. So I just combine my constants. And so that gives me my first derivative. But I'm interested in what's happening at 6. So now I want to go ahead and plug in a 6. So I get negative 675 e to the negative 0.15 times 6. So we'll crunch that number in the calculator. And we get negative 274.43. So I rounded to 2 decimals because I know that we're talking about business, which means that it has something to do with money, and money we round to 2 decimal places unless instructed otherwise. And so I need to think about what this means. And so again, sometimes it helps to think about the units. And so the units of the derivative are going to be the dependent units over the independent units. Here it's a little tricky because the dependent units is the quantity sold. So I guess we can just call it quantity. Some people like to use the word item. And then the independent variable is P, which is dollars. So per dollar. So what this is telling me is that if I charge $6 for my item, that if I increase what I charge by $1, so I'm moving 1 unit to $7, that I will sell $274 less of my product, right? So my demand is decreasing because my derivative is negative. And therefore, I really don't want to charge more money, right? Because then I'm going to sell less and less. So when we find the derivative here, we just have to be really careful because of this number up in the power. We do have to employ the chain rule, or just remember from our algebra technique before that this constant is going to come out as part of the derivative. Okay, so that was the last example on exponentials. And so today we're going to cover 2 more types. We're going to talk about the natural log type and then sine cosine type. So the next type we're going to look at is the chain rule for natural logarithms. So again, the first thing we're really looking for is to identify the type of function we're looking at. So with power functions, we had the variable in the base and it was raised to a number. With exponential functions, we had a number in the base and it was raised to a variable. With natural log functions, we have the ln of something, right? So we see that ln, which flags for us that we're talking about the natural log. And so since we have something more than just ln x here, we have this whole complicated function inside, we know that it's a chain rule. And so we're going to approach it the same way we've approached the other ones, in that we want to do a substitution to get this to look like the natural log that we know and love, which is the natural log of a single variable. So in order to do that, we employ a z substitution. So here, when we have the natural log type, our z is going to be whatever is inside the argument. So here we know that that's x to the 5th minus 3x squared plus 1 our y function, we can then simplify into the natural log of z. And again, the benefit of setting up the substitution is that we can find these individual derivatives. So the derivative of z with respect to x is going to be 5x to the fourth, that was a power rule, minus 6x, also a power rule. And then the derivative of 1 is 0 because it's a constant that's by itself. dy dz, the derivative of y with respect to z. So we think about what's the derivative of the natural log? Well, it's 1 over z. Okay. So once we have our two pieces, we want to multiply them together. Now we have to be careful here because one of the derivatives has more than one term. So I'm going to use parentheses to make sure I don't incorrectly represent it algebraically. So I have 5x to the fourth minus 6x times 1 over z, right? So I'm multiplying these two derivatives together. Now, just like last time, I don't want a z in my final answer. So I'm going to want to substitute, but I'm also going to do a simplification step here. So I'm going to multiply this first term into the numerator to separate out like what's happening. You can always write the term over 1, and then you can see why we're multiplying that into the numerator and not the denominator. So here I have 5x to the fourth minus 6x over 1 times z, which is just z, but I want to substitute back in what z represents. So I have x to the fifth minus 3x squared plus 1. So notice the structure of this derivative. We end up with one function over another function. And so it's helpful to remember that that's what we're expecting the derivative to look like for the natural log type. Okay, so I'm going to have you try one with the z substitution. So for this example, we're going to find the derivative of f of x equals the natural log of cosine x plus e to the x. Okay, so I want you to take 2 minutes and do the z substitution. Think about what z will equal, how we'll rewrite our y, what our derivatives look like, and then how we will multiply them together and how we might simplify like we did here. Okay, so take 2 minutes and then we'll go through it together. All right, take about 30 more seconds. All right. So again, our first step here is recognizing that the function we're dealing with is a natural log chain rule. So we see a cosine, we see an e to the x, but those are both inside the argument of the natural log. So that is our outer function, and that is what we are dealing with here. So we set up our substitution that z will equal whatever is inside here. So we have cosine x plus e to the x. And now we can rewrite our function as y equals the natural log of z, which is all the stuff that was on the inside. Now, when we take our respective derivatives, these come from those charts that we have. The derivative of cosine is negative sine, and the derivative of e to the x is e to the x. Hopefully these derivatives from the chart are becoming a little more second nature to you as you practice them. Sometimes you have to look them up, but after a while you start to remember them. The derivative of the natural log of z is 1 over z. So now that we have all our pieces, we're going to multiply them together. Again, the first term has more than one term, so I'm going to use parentheses. So negative sine x plus e to the x times 1 over z. And again, I'm going to bring this term into the numerator. So I have negative sine x plus e to the x over z, but I don't want a z in my final answer, so I sub back in. So I get cos x plus e to the x. So again, just like last time, I have something over something. That's the general form of what you're going to expect to see for a natural log type. Now, if we want to think about this more conceptually, what we're thinking is, okay, we're taking the derivative of the natural log of something complicated, right? So something more than just an x. So z just represents something more than the typical standard single variable. So I can think about it as I want to do 1 over whatever's in the argument, but then I have to remember to multiply by the derivative of the inside. So what does that look like on the problem we just did? Again, we started with the natural log of cosine x plus e to the x. So when I take the derivative, thinking about what I know about natural log, I can do 1 over cosine x plus e to the x, just like I do 1 over x. But what I have to remember is that I need to multiply that by the derivative of the inside. So the derivative of the inside, derivative of cosine, is negative sine. Derivative of e to the x is e to the x. And as you can see, if I were to simplify this by bringing the derivative term into the numerator, I would get negative sine x plus e to the x over cos x plus e to the x. So I get the same thing that I got before by just thinking about what I know about natural logs and thinking about how I can apply the chain rule and not miss any of the pieces. So again, this is just another method where we just have to be more careful to remember it, whereas this is a different method that's just more thorough where we write everything down. Both methods should give you the same answer every time. So let's look at some practice problems here. Okay, so we're going to try 3 different problems here on using the chain rule with a natural log. The first 2 are your standard, just find the derivative. So we're going to apply it. We're going to write it out. You can use a z substitution or you can reason through it. Either is fine. And then for the third example, we come back to our find the equation of the tangent line. So we've done this several times now. And so again, the process will be the same where we need a point and we need a slope. And what's changing is to find the slope, we need to find the derivative of a chain rule natural log. So once we have the point and the slope, we can put it all together. Okay, so I'm going to give you about 5 minutes to try these 3 problems. Feel free to work with someone near you and look back in your notes, but try these out and then we'll go through them together. All right, take about 30 more seconds. All right. So for this first one, let's try to just think through the conceptual understanding of what happens to natural logs when we think about the rate. So here, with natural logs, we know the derivative of the natural log of x is 1 over x. So if we want to apply that here, instead of 1 over x, we have 1 over whatever is inside, which is 4x to the 8th minus 2x squared. But what we have to remember is that we can't just stop there. We also have to multiply that by the derivative of the inside. So when we think about the derivative of each of these terms, the derivative of 4x to the 8th, that's going to be 32x to the 7th minus 4x. And again, the convention here is to bring that term into the numerator and write it all as one term. So we would write this as 32x to the 7th minus 4x divided by 4x to the 8th minus 2x squared. And if you did this with the z substitution, you should have got the same answer. So either written like this, or if you combined it, it would look like this. Okay, so again, we're expecting an answer with something over something. For the next one, find the derivative of y equals the natural log of 3x. This is the type of problem that students get wrong the most often with the chain rule. And even though it looks easier than the last problem, for whatever reason, a lot of times students write the derivative of this as 1 over 3x. That is not what the derivative of this is, and let's see why, okay? So let's do our substitution here. We'll alternate methods. So the inside of this function is 3x, and then we rewrite the original function as the natural log of z. Now we take each of their respective derivatives, dz, dx. The derivative of 3x is 3. That's a linear term. And the derivative of the natural log of z is 1 over z. So when we multiply these two things together, we get 3 times 1 over z. And again, we don't want a z in our final answer. We bring that 3 into the numerator, and then we substitute back in for z. So we get 3 over 3x. Well, the 3's are going to cancel, and you get 1 over x. That is not the same thing as 1 over 3x. So don't get trapped by this, looking easy. That 3 still makes it a chain rule. So we still have to make sure that if we do 1 over 3x, that's just the first step. We would still need to multiply this by the derivative of the inside, which would bring us a 3. The 3's would cancel, and we actually end up with 1 over x. So just be a little careful there. But that one is 1 over x. So whether you did it with a z substitution or reasoned through it, we should have gotten 1 over x. So the next example, we are talking again about equations of tangent lines. So again, to find the equation of a tangent line, we need a point, we need a slope. So we start by subbing in a 1 here. And we get the natural log of 1 squared, which is the natural log of 1, which is 0. So once we have our values for our point, by again plugging the x value into the original, now is where we get into the derivative. So the derivative helps us find the slope. And here I have the natural log of x squared. So I know I'm doing a chain rule here. And so I know I can do 1 over whatever that function is. So 1 over x squared, as long as I remember to multiply by the derivative of the inside. So the derivative of x squared is 2x. So simplified, I'd bring that into the numerator. So I have 2x over x squared. And I can simplify it a little bit further. So I have 1x in the top and then x times x on the bottom. So one of them will cancel, and I can simplify this into 2 over x. Now I will tell you, you don't need to do this simplification step to find the slope of the tangent line. If you plug in a 1 here or here, you're going to get the same thing. Some people like to simplify, some people don't. You should get the same answer either way. So when I plug in a 1, I get 2 divided by 1, which gives me a slope of 2. So now I have a point and I have a slope, and I'm going to put it together and see what I can do here. So y equals 2x plus b. So I plugged in my slope for m. Now I'm going to plug in my point. When x is 1, y is 0. Okay, make sure you plug the values into the right variable. That's another sort of typical mistake. If people are rushing, they just plug the number into the wrong variable and switch things. So just be careful about that. So I'm going to subtract 2 from both sides. And that'll give me b equals -2. So my final equation is y equals 2x minus 2. So again, whenever you're looking for the equation of a tangent line, you need a point, you need a slope. The slope is where the derivative comes in. The more derivatives we learn, the more different types of functions can show up here, but the process will be the same. You find the point, you take the derivative and plug in the x value to find the slope, you put it together to get the equation of the line. Okay, so those are some examples of the natural log type. The next type we're going to look at are sines and cosines. So again, we start by just looking at the form. So when we see it, we see that sine is the outermost function here, and it's sine of x cubed plus e to the x. So it's more than just sine x, and we want to simplify it, so we can do that with a z substitution. So again, we start off our process by learning how to do this with our substitution. So here, as with all of these types, your z is going to be whatever is inside the argument of the sine or cosine function. So we have x cubed plus e to the x. Then we're going to rewrite our y function with the z in it. So the simplified version, sine z. We want to write it that way because we know how to take the derivative of sine z since it's a single variable. We are going to find the derivative of each piece. So dz dx, the derivative will be 3x squared plus e to the x. Again, since these are separated by addition, I take the derivative of each piece. And then dy dz, the derivative of sine is cosine. So now that I have my two derivatives, I'm going to multiply them together. And again, because my first derivative has two terms, I'm going to use parentheses so I don't algebraically misrepresent this. So I have 3x squared plus e to the x times cosine of z, but I don't want a z in my final answer. So I have 3x squared plus e to the x times cosine, and now I substitute back in for z, I have x cubed plus e to the x. So something I want to point out here that's similar to exponentials. So the argument of sine was x cubed plus e to the x. The argument in the derivative of cosine is x cubed plus e to the x. What's inside the trig function didn't change. What changed was what was outside the trig function, and then we had to multiply something on. Okay, so just kind of keep that in your back of your mind here. So I want you to try this next one. So we have the function f of x equals cosine of x to the 6th. So I want you to set up a z substitution. Think about what's our z here, what's our y going to be, find each of the derivative pieces, and then multiply those together. Okay, so I'm going to give you about 2 minutes. Try this out, write out your steps, and then we'll go through this one together. right, take about 30 more seconds. All right. So again, with our z substitution, we're thinking about what is in the argument. So here, my z is going to be x to the 6th. And my outside function, I rewrite as y equals cosine of z, because z represents what was inside. Now I need to find each of their respective derivatives. So dc dx is going to give me 6x to the 5th. And now dy dz, the derivative of cosine is negative sine z. So don't forget that negative. It's easy to forget which one gets the negative. The derivative of cosine is negative sine. So now I need to multiply these together. So I have 6x to the 5th times negative sine z. Again, I don't want a z in my final answer. So I'm going to do two things here. I'm going to substitute in for z, but I'm also going to pull that negative sign to the front. So I have negative 6x to the 5th times sine of z, which is x to the 6th. So again, what was inside the argument didn't change. What changed was the outside function, and then we multiplied by something. Okay. So again, we can think about it also conceptually and what we know is happening with sine and cosine. So if we're thinking about taking the derivative of sine of something complicated, we know that we're going to get cosine, right? That sine turns into cosine. So what we have to remember is that the argument does not change when we take the derivative, and we have to multiply by the derivative of the inside. So sine turns into cosine, and then multiply by the derivative of the inside. Similarly, cosine will turn into sine with a negative in front and a multiplication in the back, which is the derivative of the inside. So thinking about the problem we just did, okay, we think, okay, I know that cosine turns into negative sine, right? The inside doesn't change. But I have to remember to multiply that by the derivative of the inside. So I have to remember to multiply by this extra term, right? So this is the change that was made, but then also this extra piece. And again, we will normally bring constants to the front. So we would end up bringing this whole term to the front. Okay. And so I'm just talking about the order because if you're taking a mini quiz and it's multiple choice, I just want to make sure that you know that if you got an answer that looks like this, that this is the same thing so that you can find it on the mini quiz. Okay. So now that we know how to think through it, let's do some practice problems with sine and cosine. So we're going to do 3 problems here. So the first 2 are going to be computational, where we're just practicing the chain rule, right? So you can do a z substitution. You can just think through it conceptually. Either one is totally fine. And then for the third problem, we have an application where we see that we would need to take the derivative of a function that includes the sign. And this particular function is a chain rule because of this pi over 4. If the pi over 4 wasn't there, we could just take the derivative of sine normally, right? If we just had sine of t, but the pi over 4 turns it into a chain rule. So I'm going to give you about 5 minutes to try out these 3 problems. Again, you don't have to try them in this order. If you want to start with the word problem and then the other ones, that's fine. But try them out, see what you can figure out, and then we'll go through them together.
All right, take about 30 more seconds. All right, so let's start with this one. So here, we'll reason through this one and see if we can figure out how to think about this sort of holistically. So we know that the derivative of sine is cosine. So what we have to remember is that everything inside stays the same. And what changes is this outside part. But then we also have to remember that we need to multiply this by the derivative of the inside. So we look at the function that is inside the argument and we think about what the derivative is going to be. So we have 16x cubed plus now the derivative of x squared is 2x. So our full derivative looks like this, should have these two pieces. If you did a z substitution, those should be the two pieces that you have that are multiplied together. They may be in the other order, but those are the two terms. Okay. Let's look at example 3, and we'll do this one with a z substitution. So here we have the cosine of the natural log of x. So here my z is going to be what's on the inside, so the ln x. And so my y becomes cosine of z.
Now we're going to take the derivative of each term. So dz dx, the derivative of the natural log is 1 over x. And then the derivative of cosine, dy dz, derivative of cosine is negative sine c. Okay, so then we want to multiply these two things together. So we have 1 over x times negative sine z. We don't want a z in our final answer. And again, I'm going to bring this term into the numerator. So I have negative sine, and I go fill back in what z is. So natural log of x divided by x. So our derivative looks like this. You can leave the 1 over x outside, it's up to you. But again, a reminder, the inside of the argument doesn't change. So the inside of the argument was natural log of x, and it's still natural log of x. It's the outside that changed. Okay. So now let's look at our application. So during one particular day, the value of a stock, V of T, for Math Inc. opened at $45 a share at 9 a.m. and closed at $45 a share at 5 p.m. It varied periodically during the day with time T in hours since 9 a.m. So that's going to be important. So I'm going to underline that. And we can model it with this function here, V equals 38 sine of pi over 4t plus 45. Find the rate, so that's derivative, find the rate at which the value of the stock is changing at 1 p.m. So the word rate indicates to us that we're looking for a derivative. So before we deal with the 1 p.m. piece and figuring out what to plug in, we first need to find the derivative of this function. Okay, so there's two pieces to the original function. There's the 38 sine of pi over 4t, and then there's a plus 45. So I just want to point out that the 45, the derivative is 0. So that piece is going to disappear. So when we look at the first part, the 38 is a constant multiple. So I have 38 times, and now the derivative of sine is cosine. So I have cosine of the same thing, pi over 4t. But now I need to remember to multiply that by the derivative of the inside. So if you have a number times t, the derivative is just that number. That's our linear term rule. So times pi over 4. So my first derivative looks like this. And remember, t is my variable, and I'm interested in what's happening at 1 p.m. It would be really easy for me to think I should just plug in a 1 if I was just sort of rushing. But I want to point out here that time is in hours since 9 a.m. So to figure out my t, I have to figure out how many hours is between 9 a.m. and 1 p.m. So that means I'm actually considering what's happening at time equals 4. So be really careful about that piece, because that is easy to get lost when you're sort of really only thinking about derivatives. So I have to plug in a 4 here. So I'm going to have pi over 4 times 4, all times pi over 4. Again, just as a reminder, when you are plugging in sines and cosines into your calculator needs to be set to radians in order for you to be getting the right answer here. So I get negative 29.85. So that means at 1 o'clock, the stock is decreasing, right? My derivative is negative and it's losing value. It's losing about $29.85 every hour that goes on at this given time. So I can tell at this point my stock is decreasing. And we know that cosine increases and decreases. So this is one of the points on that cosine graph where we're in the downward direction. Okay, so this might be an example of why we would want to use a chain rule with the sine or cosine to sort of figure out what's happening with a particular model during a certain span of time. So now we've looked at each type individually. So we had the power rule, we had the exponential rule, we had the logarithms, and we have sine and cosine. The piece that we haven't done yet is looked at what would happen if we had more than one of these rules together, right? And so when we start thinking about that, things with multiple chain rules. What's going to become really important is that first step where we looked at a function and we looked at what type it was to figure out how to apply the chain rule. So the same thing's going to happen when you have multiple functions. We have to look at the function and figure out what is the outermost function that is dominating this particular function, and then start with that type and work our way through. So we're going to look at some examples of multiple chain rules. And I want to sort of give you a forewarning that the first time you do some of these, they can be really intimidating, especially if you haven't had a lot of practice with sort of the single types. And so these are on a difficult end of this spectrum. So if you're like, wow, this is really difficult. Yes, it is. But as you get to know the different types really well, this becomes more easy. So it won't be easy today, right? We're going to go through it. We're going to try it. But as you practice more and more chain rules, then you start to see how these all interact with each other. Okay, so all that to say, don't let this scare you, because you will be able to do this after you've practiced a bit if it seems a little hectic today. So our plan here, we're going to do the first one together, and then I'll have you try the second one. So here is my big function, right? All the parts that I'm looking at. And I need to look at this and figure out what is my first type, right? And so what's really sticking out to me here is this 10. And I notice that I have this parenthesis all raised to the 10 power. So my variables are all in the base, and that's all raised to the 10th power. So I'm starting with a power function, okay? So when I think about the power function and I think back about how we sort of work through that, I remind myself that, okay, I can deal with that 10 power first and leave everything inside the same, and then multiply by the derivative of the inside. So the derivative of the inside I'll deal with in a few minutes, but let me just start with this power of 10, okay? So the 10 comes down in front. Everything inside stays the same. So I just carefully write everything down as I go. I'm just copying it from above. Okay. And then I have to the 9 power. So all I did here was I put the 10 in front and I subtracted 1 from the power. Everything inside stays the same. Okay, so now that I've dealt with that piece of it, I have to now multiply that by the derivative of the inside. So now I look at the inside function. I ignore the 10 and I say, what kind of type is the inside function? And the inside function, I notice, is a natural log. And so, okay, my next type is the natural log type. I know from the natural log type that I can do 1 over whatever is here, and then I multiply that by the derivative of the inside. So I'm going to go ahead and in the denominator, just write down what's in the argument. So x cubed minus e to the 2 to the x minus x cubed plus 1 plus 6. So 1 over that times the derivative of the inside. I know that the derivative of the inside is going to end up in the numerator. I'm going to leave that open. So the inside is just the stuff that's in this argument of the natural log. So I have to do the derivative of that. So the derivative of x cubed is 3x squared. The derivative of 6 is 0. That's going to go away. But the derivative of this e term is now another chain rule because I have e to something complicated. So I think back to my exponential type and I say, okay, I have e to the 2 to the x minus x cubed plus 1. I know I'm going to get the same thing back times the derivative of the power. So I go to the power and I say, okay, derivative of 2 to the x, 2 to the x, ln 2, derivative of x cubed, 3x squared, derivative of 1 is 0 because it's a constant. And so my entire derivative is this entire thing, okay? This one has almost every single type we've looked at without sine or cosine. This one is incredibly detailed. Like I was like, how can I throw in enough chain rules that we're hitting a lot of things? So part of this process is just getting really comfortable with the derivative pieces and types, but then also being able to work through the types as you go if you encounter another chain rule. So again, this takes practice, it takes organization. That's why we're starting today. If it's taking a while for you to get these pieces, that's totally fine. That's totally normal. And so I'm going to have you try the second one, which is e to the x cubed minus 2 natural log of 5x to the 8th, all raised to the 16th power. Okay, so again, I want you to start this by thinking about what is the main type that I'm looking at here, right? Is it a power rule? Is it exponential? Is it log? Is it sine or cosine? Once you figured that out, then you just start applying the rule to it, and within that, more derivatives come out. Okay, so I'm going to give you about 3 minutes to try this one, and then we'll go through it together. Again, don't worry if you're feeling overwhelmed or if you're not getting it right. These do take practice, and you will get it once you've done more of these on homework and on the quiz and things like that. If you are getting it, great. Okay, but we'll try it out, and then we'll go over it in about 3 minutes. All right, take about 30 more seconds. All right. So when we look at this and we think about where the variable is in a power and not a base, right? We have e to this craziness, but the variables are up here. So this is an exponential type, and we want to use our exponential map to start figuring out this derivative. So for exponentials, we know we're going to get the same thing back first. So I'm just going to write down exactly what I started with. So e to the x squared minus 2 ln 5x to the 8th, all raised to the 16th. And then I know that I have to multiply that by the derivative of the power. So here, when I do that part, I'm going to focus in on what is going on in the power. And what I notice when I look at the power is that if I'm just considering that by itself, now the variable's in the base, right? I have something raised to the 16th power. So to take the derivative of the piece that's right here, I have to use a power rule because I have this parentheses to the 16th power. So for the power rule, the 16 comes down, everything inside stays the same, and I subtract 1 from the power. Okay, so when I do that part, that's dealing with the outside part, but I still have to multiply that by the derivative of the inside. So I think about what's inside these parentheses, and I have to multiply by the derivative of that. So starting with x cubed, I get 3x squared minus, now this next term, this 2 ln of 5x to the 8th. I want to do that separately because there is some simplification that's going to go into this, and I want to make sure that you see why. So here, the 2 is a constant multiple. But now the natural log says take whatever is in the argument. You're going to do 1 over that. So 5x to the 8th. And then multiply that by the derivative of the inside. So the derivative of this term is going to be 40x to the 7th. Okay. So when I simplify this, I get 40 divided by 5, which is 8. And 8 times 2 gives me 16. So I have 16, and then here, x to the 7th over x to the 8th. I have 7 x's multiplied together on the top and 8 on the bottom. So all 7 from the top will cancel with 7 of them from the bottom, leaving just 1 on the bottom, which is 16 over x. So here, this piece becomes 16 over x once that derivative piece is simplified. So my full derivative, again, looks like this. So whether you got some of these pieces or all of these pieces, the more you practice, the easier these become. And they're not easy at first. It does take practice. You do have to put in a little time to really think about it. But the more organized you are when you do these, the better off you are in terms of not missing things and things like that. I do strongly encourage the use of parentheses when appropriate, because it's really easy to drop them and then things get all sorts of crazy. So that is the end of the chain rule. We're going to stop here. Next week, we'll go into the rest of chapter 3, but I strongly, strongly recommend that you try as much of the homework as you can before you do the mini quiz for the practice. Okay, have a great rest of your day, and I will see you guys on Tuesday.